Imagine standing in a sealed, pitch-black room. No matter how wide you open your eyes, the chair right in front of you is completely invisible. In the absence of sensory information, you are functionally blind to the physical matter around you. Now, flick a switch. Instantly, the details of the room flood in. Look out the window, and you clearly see the tree outside. The chair and the tree didn't suddenly manifest out of thin air. They were sitting there. So what exactly traveled the physical distance between that tree outside and your eyes inside to trigger the image in your brain? The answer is a physical traveling entity, light. It acts as an invisible courier, picking up visual data from the physical environment and carrying it across space directly to your retinas. We never actually see the physical objects around us. We only ever see the messenger. The journey of this messenger starts at a source. That could be the sun, a flame, or the bulb in your ceiling, emitting energy outward into space. As that light travels, it encounters everyday physical objects, like the tree outside your window. These objects act as passive relay stations in the environment. This schematic shows how that relay works. A beam travels from the sun, hits the tree, and bounces off toward your eye. We call this reflection. The exact angle determines whether that beam makes it into your pupil or misses entirely. Some materials, like clear glass, are transparent. Instead of forcing a bounce, they allow the light to pass straight through, which is why we can see through them. Without this specific geometric bouncing mechanism, every object outside of a direct light source would remain entirely invisible to us. Knowing that light bounces is only the first step. We also have to map how it actually moves through space to reach those objects. In optics, we use the ray model. A ray is simply a perfectly straight line, representing the rigid path light takes in our everyday world. The most definitive proof of this rule is a phenomenon you see every day, a shadow. In this visualization, parallel rays of light hit a solid, square object. Because a ray cannot steer itself or curve around the edges, the blocked lines create a sharp, geometric absence of light directly behind the obstacle. The existence of crisp shadows is the undeniable proof that light cannot walk around everyday obstacles. It is locked into a straight-line path. There is, however, an exception. What happens if the object blocking the light ray isn't a tree or a wall, but something incredibly tiny? When an opaque object becomes microscopically small, the light stops acting like a straight line and begins to ripple and curve outward around the edges. This specific edge-bending effect is known as diffraction. This tiny bending proves that light has a complex, dual nature, acting as both a wave and a stream of particles, a finding that forms the foundation of modern quantum theory. While the quantum world exists at the microscopic level, for the scale of our everyday lives, rooms, trees, and mirrors, the straight-line ray model is perfectly adequate and entirely reliable. We have our basic mechanics. Light is emitted, it travels out as perfectly straight rays, and reflects off objects into our eyes to create vision. Because light travels in predictable straight lines, we can mathematically predict where it will go. And if we can predict its path, we can control it. By polishing a surface to a high sheen, we strip away random scattering, allowing us to dictate the exact angle of the bounce. This diagram shows the power of a spherical mirror. If we curve the reflecting surface inward into a concave shape, we can force all those straight parallel rays to bounce toward a single intersection point. Manipulating this focal point allows us to concentrate sunlight to produce intense heat in solar furnaces, or to create the large, magnified images used in a dentist's mirror. Understanding the straight-line rules of light gives us the ability to actively hack visibility. This gives us the exact toolset we need to map the geometry of spherical mirrors. Every morning, you stand in front of a piece of glass, and it perfectly copies your every move. But what is actually happening in that millimeter of space where light meets glass? To figure that out, we need to strip away the sink, the room, and even you, leaving just a flat two-dimensional line to represent the mirror. Before we can build an entire reflection, we have to look at the smallest unit of this process, a single isolated ray of light hitting that surface. Draw a perpendicular line from the mirror, called the normal. The incident ray's angle is measured from this normal. The reflected ray leaves at the exact same angle, the first law. In 3D, all three lines lie perfectly flat against a single plane, the second law. These two geometric rules govern how light interacts with any reflecting surface. They are the building blocks for the more complex optical phenomena we will explore later. Place a lit candle before a mirror. Light rays strike the glass and bounce into an observer's eye, diverging. Your brain assumes light travels straight, tracing those rays backward through the mirror. Where they meet, an image forms. Is this image real or virtual? The answer is virtual. No physical light rays ever pass through the wall behind your bathroom mirror. The image exists solely as a geometric projection constructed inside your mind. First, the image is virtual. Second, it stays right side up, called erect. Third, it shares the exact same height and width. Fourth, mirrors swap left and right, called lateral inversion. Finally, the image forms as far behind the mirror as the object in front. Virtual, erect, same size, laterally inverted, and equidistant. These 5 properties define every reflection you see in a plane mirror. This consolidated cheat sheet shows the entire framework we just built. You have the 2 geometric laws of reflection on the left and the 5 properties of plane mirror images on the right. As long as you remember to measure your angles from the normal and recognize that a flat surface creates an identical virtual projection, you can solve any plane mirror problem. But what happens to these neat, parallel projections when you warp the surface? If the mirror curves inward like a bowl, the reflected rays are forced to cross paths. The laws governing a single light ray remain true, but changing the physical geometry of the glass unlocks a new world of optics. We will map those spherical mirrors in the next lesson. Grab a shiny new stainless steel spoon and take a look at your face. Spoon mein apna chehra to dekha hi hoga. Keep it close and you look slightly distorted, maybe a bit wider than usual. But as you slowly pull the spoon away, your reflection stretches, warps, and then, ekdam se, flips completely upside down. Turn it around to the backside and you're suddenly right side up again, but tiny. This piece of cutlery houses 2 distinct optical tools. One side curves inward, while the exact opposite surface bulges outward. These distortions follow the strict mathematical rules of spherical mirrors. To understand why your face flips, we have to look past the reflection and map out the mirror's hidden anatomy. Imagine these mirrors as a chunk cut from a perfect hollow sphere. We slice that section right off. The side curving inward, like a cave, is the concave mirror. Flip that glass over so the surface bulges outward, and it becomes a convex mirror. You rely on these shapes daily. Concave mirrors provide the highly magnified view needed for shaving. Convex mirrors allow drivers to easily see a wide view of the traffic behind them. Whether the glass curves in or out changes how it bends light. Predicting that movement requires locating invisible structural points. We mark the center of the glass as the pole, P. The full sphere's absolute center floating in space is the center of curvature, C. The distance between them is the radius of curvature, R. A line extending through both creates the principal axis. This framework of P, C, and the principal axis dictates exactly how light behaves upon striking the glass. You might have seen this geometry if you ever aimed a concave mirror at sunlight, until a tiny, blindingly bright, concentrated dot of light instantly and violently burned a hole straight through a piece of paper. When parallel sunlight hits a concave mirror, the angled glass forces the reflected rays to crash together. They intersect at a single point on the principal axis, the principal focus, F. The distance from the pole to this focus is the focal length, F. Now, a convex mirror scatters parallel light in different directions. These rays never physically meet in front of the glass. Instead, they trace back to a virtual focus hidden behind the mirror. When you harness this focal power at an industrial scale, you get a solar furnace. These massive curved walls of glass catch sunlight and bounce it into a single focal point hot enough to melt steel. Locating and controlling that exact focus is what turns a curved piece of glass into a tool that manipulates raw energy. Let's lay all these pieces out together. We have our mirror at pole P, our center of curvature at C, and our focus at F. If you measure these points, you find an elegant geometric truth. The focus, F, always sits exactly halfway between the mirror's surface and its center of curvature. This gives us the foundational equation for spherical mirrors, R equals 2F. The total radius of curvature is exactly twice the focal length. Because engineers know R always equals 2F, they can reverse the whole process. By placing a bulb exactly at the mirror's focal point, as seen in this searchlight, the curved glass throws the light outward in perfectly parallel lines, punching a solid beam through the darkness. We have the map. In the next video, we are going to place an object onto this map and slide it through the focus. That is when the reflection looking back at you decides to shrink, magnify, or flip completely upside down. We've seen how drawing ray diagrams helps us locate where an image will form, but drafting perfect lines every single time is slow. To calculate these positions instantly, we shift from drawing physical geometry to using algebra. Equations allow us to calculate where an image will appear, how big it will be, and whether it's upright or inverted, without ever touching a ruler or a protractor. To make the math work, we need a universal set of rules called the new Cartesian sign convention. We start by taking our mirror and placing it on a standard XY coordinate graph. The mirror's pole, labeled P, sits directly at the origin 0, 0, and the principal axis runs right along the x-axis. Our first fixed rule: the object is always placed to the left of the mirror. Because it sits on the negative side of the x-axis, the object distance, represented by the letter U, is always a negative value. From the pole, any distance measured to the right along the x-axis is positive. Any distance measured to the left is negative. The same logic applies to height. Distances measured upward, perpendicular to the principal axis, are positive. These are erect objects. Distances measured downward are negative, which means the object or image is inverted. This gives us strict rules for focal lengths. A concave mirror curves inward, placing its principal focus in front of the mirror on the left, giving it a negative focal length. A convex mirror curves outward, placing its focus behind the mirror on the right, meaning its focal length is always positive. If we don't assign these positive and negative signs correctly before we start calculating, the formulas will output positions and sizes that do not match physical reality. With our signs established, we can use the mirror formula. 1 over v plus 1 over u equals 1 over f. To use this, we map these letters to their physical distances. V is the image distance, u is the object distance, and f is the focal length. This equation works for all spherical mirrors, in all situations, but only if you plug in the numbers using the exact Cartesian rules we just covered. Knowing where the image forms is step 1. Step 2 is knowing what it looks like. Magnification, represented by the letter M, compares the height of the image, h', to the original object height, h. We can also calculate it using distances. M equals negative v over u. The magnification number gives us two separate pieces of information. First, we look at the sign. A negative sign tells us the image is real and inverted, formed below the principal axis. Conversely, a positive sign means the image is virtual and erect, standing upright above the axis. Next, we ignore the sign and look at the number itself. If the value is less than 1, like 0.5, the image is diminished. If it's greater than 1, like 2.0, the image is enlarged. By separating the sign from the magnitude, magnification defines the orientation and relative scale of the image. Let's put this into practice with a textbook example. We have a convex rear-view mirror with a radius of curvature of 3 meters. A bus is located 5 meters from the mirror. Before we calculate the image position, what are the correct signs for these values? Because it's a convex mirror, its focus is behind the mirror, so the radius and the focal length are positive. The bus is the object, sitting in front of the mirror, so the object distance u is negative 5 meters. We plug these into our rearranged mirror formula. We have 1 over 1.50 minus 1 over negative 5.00. Notice the double negative. Subtracting a negative combines into a positive, which is a common place to make an arithmetic error. Solving the fractions gives us a final image distance, v, of positive 1.15 meters. That positive sign indicates the image is formed behind the mirror. Let's run a concave mirror problem. This time, our focal length is negative 15 centimeters, and our object distance is negative 25 centimeters. After using the mirror formula to find the image distance, we calculate the magnification and get a result of negative 1.5. The negative sign means the image is real and inverted. The 1.5 means the image is 1.5 times larger than the object. By strictly following the sign convention, the mathematical result aligns with the physical outcome we would observe in a lab setting. These tools are all you need to solve spherical mirror problems. Master the Cartesian positive and negative zones on the left and plug those values into the formulas on the right. Keep a close eye on your signs during calculations, and the math will handle the heavy lifting. Up next, we'll apply these exact same rules to light passing through lenses as we explore refraction. Sunlight cutting through a dusty room follows a predictable path. It is perfectly straight. Our brains rely on this specific physical behavior to navigate reality. We trust our eyes because we assume light never detours on its way to us. But that assumption fails the moment we look at a glass of water. When a pencil is lowered into the water, the solid wood appears to snap and shift right at the surface. You can see this happen with a coin as well. Place one in an empty bowl and move back until the rim just blocks it from view. As you pour water in, the coin seemingly rises from the bottom and becomes visible again. The objects haven't moved, but our perception of them has. To understand why our eyes see a glitch through transparent materials, we have to look at the physical boundary where they meet. This visual shift is a physical phenomenon known as refraction. It occurs whenever light ray crosses the border between two different transparent substances. We map this with a ray diagram. The straight incident ray travels through air, hitting the water. We use a perpendicular reference called the normal line at the point of impact. The light ray then angles downward, bending closer to this normal line. This change in direction is tied to a change in speed. As light crosses from the air into water, it slows down, and this drop in velocity dictates the angle of the new path. The way light bends at these borders isn't random. It follows a specific set of geometric requirements. The first law of refraction states that the incoming light, the perpendicular normal line, and the newly bent ray all exist within the same two-dimensional plane. To find the exact angle of the bend, we use Snell's law. This formula shows that the ratio between the sine of the angle of incidence and the sine of the angle of refraction is always a constant value for any two materials. Snell's law allows us to predict the path of light with total accuracy. It shows that the relationship between these two materials is consistent and measurable, regardless of the angle of the incoming light. That constant value in Snell's law represents a specific property of a material, called its refractive index, often denoted as n. This is a ratio of light's speed in a vacuum compared to its speed in the material. If light enters a medium and its speed v drops, the refractive index n goes up. To see why a speed change forces a turn, imagine a car driving off a smooth road into thick mud at an angle. The first wheel to hit the mud slows down instantly, while the other wheels are still moving fast on the pavement. That difference in speed pulls the entire car into a turn. This ability to slow light is called optical density. It is important to distinguish this from mass density, how much an object weighs. Take water and kerosene as an example. Kerosene is physically lighter and floats on water, but it has a higher refractive index of 1.44. Because it is optically denser, it slows light down more and creates a sharper bend than water's 1.33 index. Diamond represents the extreme end of this scale. With a refractive index of 2.42, it slows light down significantly. The light rays are bent so severely inside the stone that they reflect and scatter, creating the iconic brilliance we see from the outside. We can now apply these mechanics to the illusions we started with, starting with an object submerged in a pool of water. When light leaves the submerged object and hits the surface, it moves from water into the rarer air. The light speeds up and bends away from the normal line as it travels toward your eye. Because our brains are hardwired to believe light only travels in straight lines, we trace the angle of that light backward. We perceive the object at a shallower point than where it actually rests. The broken pencil and the rising coin are the byproduct of a brain that cannot perceive a change in speed. We experience these physical displacements because our biology assumes a straight path that simply isn't there. A final way to test these rules is through a rectangular glass slab, which forces light to cross two boundaries in a row. At the first border, light enters the glass from the air. It slows down and bends toward the normal line, moving deeper into the slab. When it hits the bottom border, the process reverses. The light enters the rarer air, speeds back up, and bends away from the normal line. Because the sides of the slab are parallel, the two bends cancel each other out. The light exits the glass traveling in the exact same direction it started, though the refraction has shifted its position slightly to the side. This experiment summarizes the core of refraction. It is a change in direction caused by a change in speed, measured by the refractive index, and perfectly predictable through Snell's law. By understanding how light behaves at these flat borders, we can begin to look at what happens when the glass itself is curved, moving from simple refraction to the engineering of lenses. Navigating heavy gridlock is a constant exercise in spatial awareness. When vehicles are inches apart and moving at varying speeds, your safety depends on knowing exactly where everyone else is at every single moment. But every car has a hidden weakness, the blind spot. This is the area behind and to the side of your vehicle that your natural line of sight simply cannot reach. You might assume a standard flat mirror would solve this, but the geometry says otherwise. Because a flat plane reflects light at a very narrow, restrictive angle, it creates a tunnel vision effect that misses cars traveling in the lanes right next to you. To bridge that visual gap, engineers use a specific optical tool, the convex mirror. You've seen the result of this choice etched into the glass of nearly every side view mirror on the road. Objects in mirror are closer than they appear. This warning exists because of a deliberate optical trade-off. It is a calculated design choice that prioritizes a wider view of the road over a perfectly scaled image, and the secret to how it works lies in the physics of the curve. Physically, a convex mirror is a slice of a sphere with the reflective coating on the outside. It bulges toward the light source, curving away from the mounting. We define its orientation using a horizontal principal axis. The exact center of the mirror surface, where this axis strikes the glass, is called the pole, or point P. If we were to complete the circle that this curve belongs to, we would find the center of curvature, labeled C. In a convex mirror, this center point actually sits behind the reflective surface. When light rays from a very distant source hit this outward bulge, they don't bounce straight back. Instead, they scatter, diverging away from each other as they reflect. However, if we trace those scattered rays backward through the mirror, they appear to originate from a single point. This is the principal focus, F, located exactly halfway between the pole and the center. Because the light only appears to meet at this point behind the glass, we call this a virtual focus. For light coming from a great distance, the curve concentrates that entire image into a tiny, point-sized reflection. Now, let's look at how this applies to a car on the road. We'll place an object at a finite distance in front of the mirror to see how its image is formed. We trace the first ray parallel to the principal axis. It strikes the mirror, reflects outward, and traces backward to that virtual focus point, F. The second ray is aimed directly at the center of curvature, C. Because it strikes the curve at a right angle, it reflects straight back on its own path, continuing the trace towards C behind the glass. Where those two traces intersect behind the glass is exactly where the image forms. The geometry reveals the three golden rules of a convex image. It is virtual, it is erect, meaning upright, and it is diminished, or significantly smaller than the real object. This remains true regardless of distance. As a car moves closer to your bumper, the image grows slightly, but it stays upright and shrunken, permanently trapped between the pole and the focus. This consistency is vital for driving. Because the geometry never allows the image to flip upside down, the reflection is always upright and predictable. This brings us back to the side view mirror on your car. Why would engineers choose a mirror that intentionally shrinks the world? The answer is field of view. A flat mirror can only show you what is directly behind you, but the outward curve of a convex mirror captures light from a much wider angle, effectively giving you a massive cone of vision that covers the lanes beside you. To fit that massive amount of visual information into a small piece of glass, the mirror has to shrink the image. That shrinking process is the reason for the safety warning. Our brains use the size of an object to estimate its distance. If a car looks small in the reflection, your survival instincts assume it must be far away. The warning is a constant reminder to override that instinct. The car in the next lane only looks small because the mirror's curve compressed it to give you a wider view. In reality, it's much closer than your eyes are telling you. Virtual, erect, and diminished. These are the geometric properties that make the modern side view mirror possible. The convex mirror sacrifices true scale to give us a life-saving wide field of view. In our next episode, we'll move from the diagrams to the data, showing you how to use mirror formulas and sign conventions to calculate the exact position of these images. You do the algebra perfectly and plug in the right numbers, but the final answer is still wrong. In optics, a single missed negative sign is often the culprit. The new Cartesian sign convention treats the mirror like a math grid, placing its pole at the origin. Since incident light travels left to right, everything right of the pole is the positive x-axis, and everything left is the negative x-axis. Vertically, the logic is the same. Distances measured perpendicular to and above the principal axis are positive, while those measured below are negative. Setting the mirror on a grid this way provides a physical reference point for every measurement we'll make moving forward. We can apply this spatial logic immediately to determine the focal length for different types of mirrors. Tracing the curve of the concave mirror shows its sphere completes on the left. This places its principal focus on the negative side of the grid. Because its focus physically sits to the left of the origin, the focal length for a concave mirror is negative. For the convex mirror, the curve completes the sphere behind the reflecting surface. This puts its focus on the right side of the grid. Since the center of a convex mirror is on the right, its focal length is always positive. Consider an object placed in front of a mirror that forms a virtual, erect image behind it. Look at where this image sits on the grid. Based on its position, would the image distance, v, be positive or negative? Because the virtual image forms behind the mirror on the right side of the origin, the image distance is positive. There is one variable that requires specific attention because it behaves the same way in almost every problem, the object distance, u. The object is always placed on the left so light can fall on the mirror. This means the object distance is universally negative. When a problem says an object is 10 centimeters away, the negative sign must be added manually before you begin your calculation. We can consolidate these rules into a single map. Grounding these signs in a simple graph makes them much easier to recall during a test. The object is on the left, so u is always negative. Concave mirrors curve left, making their focal length negative. Convex mirrors curve right, making theirs positive. Real images form on the left, so they are negative. Virtual images form on the right, so they are positive. Consistent signs are the foundation for the mirror formula. With this map, you're ready for the calculations in our next lesson. We can calculate an image's location and size using simple algebra, bypassing the need to draw complex ray diagrams for every scenario. This equation is the mirror formula. It states that 1 over v plus 1 over u equals 1 over f. The blue u represents the object distance, how far the physical item is from the mirror's pole. The green v is the image distance, and the yellow f is the mirror's focal length. To solve for these, we use the new Cartesian sign convention. Under these rules, the object distance u is always negative because the object is placed in front of the mirror. The signs for v and f will change depending on the mirror type and the image's position. This formula creates a mathematical link between the physical placement of an object and the resulting position of its reflection for all spherical mirrors. While the mirror formula provides the position, magnification describes the relative size of the image compared to the object. The standard calculation for magnification, m, is a ratio, the height of the image, h', divided by the height of the object, h. Magnification is also related to the distances we used earlier. It can be expressed as negative v divided by u. Pay close attention to that built-in negative sign when substituting your values. The sign of your final result describes the image's nature. A negative magnification indicates the image is real and inverted, while a positive result means it is virtual and direct. Combining these two sets of formulas allows us to construct a data-driven model of any reflection. Let's apply them to a practical problem. Take a convex rear-view mirror on an automobile. If a bus is located 5 meters away and the mirror has a radius of curvature of 3 meters, we can determine exactly what the driver sees. First, we extract our knowns. The radius is 3 meters. Since the focus of a convex mirror lies behind the reflecting surface, the focal length is positive 1.5 meters. The bus sits in front of the mirror, so U is negative 5 meters. We rearrange the mirror formula to isolate 1 over V, then substitute our values for F and U. Note the double negative here. Subtracting the negative 5 meter fraction results in these two signs colliding to become a positive. After resolving the fractions, we find the image distance V is positive 1.15 meters. Using that V value in our magnification formula, M equals negative 1.15 divided by negative 5, which results in positive 0.23. The positive V tells us the image is 1.15 meters behind the mirror. The positive magnification, being less than 1, shows the image is erect and shrunken to about 1/4 of its original size. Now we'll apply both formulas to a concave mirror setup to find the image's position and its specific physical height. A 4 centimeter tall object is placed 25 centimeters in front of a concave mirror with a 15 centimeter focal length. Object distance, U, is negative 25. For a concave mirror, the focal length is also negative, so F is negative 15. We set up the rearranged formula. Once again, the subtraction of a negative object distance creates a positive term in our calculation. Pause the video here to calculate V yourself. Find the common denominator, solve the equation, and resume when you have the answer. Using 75 as the common denominator, the algebra resolves to an image distance of negative 37.5 centimeters. To find the image height, h', we can bridge our magnification equations, setting the ratio of heights equal to the negative ratio of distances. We substitute our values, making sure to track each negative sign. This gives us an image height of negative 6 centimeters. These results represent the physical reality of the reflection. The negative V means the image forms in front of the mirror, making it real, and the negative height indicates the image is inverted. Use this summary as a reference for your next set of problems.
Take a perfectly straight, solid pencil. When it's lowered into a glass of clear water, the stem appears to cleanly snap at the waterline. Or try placing a coin at the bottom of an empty bowl. Back away just until the rim blocks your view of the coin, and then slowly pour water in without moving the bowl. The coin will drift right back into your line of sight. Our visual processing relies on a specific rule. Light travels in straight lines. That rule is how we make sense of shadows, depth, and the shape of the world around us. These observations prove that the water physically intercepts the light, altering its path before those rays ever reach our eyes. We call this fundamental property of light refraction, the bending of light rays as they cross the boundary between two different transparent materials. For refraction to occur, light has to travel obliquely, meaning at a slight angle, from one transparent medium into a different one. If it hits the boundary dead on, it passes straight through, but if it hits at an angle, its direction changes. The reason for this bend comes down to a property called optical density. In a vacuum, light moves at 300 million meters per second, but as it enters an optically denser material, like glass or water, it encounters resistance and slows down. We can predict exactly how this speed change affects the direction. Let's draw an imaginary perpendicular line, called the normal, right at the point where the light hits the boundary. When a light ray moves from a rarer medium into a denser one, it slows down and bends toward that normal line. Conversely, when that same light ray reaches the other side and exits back into the air, a rarer medium, it speeds back up. This increase in speed causes the ray to bend away from the normal line. The change in velocity at the physical boundary is the sole mechanism that dictates the angle of the resulting bend. Now we can apply those exact rules to the mystery of our broken underwater pencil. To see the submerged tip of the pencil, light originating from that tip must travel upward through the water toward your eyes. Water is optically denser than air. As that light ray reaches the surface boundary and enters the rarer air, it speeds up and bends away from the normal line before reaching your retina. Your brain interprets these signals by assuming light always travels in a straight line, without accounting for the bend at the water's surface. Your visual system traces the light backward along its final angle,
projecting a phantom tip that sits higher and to the side of the actual pencil. The pencil appears displaced solely because our brain projects an unbroken straight path onto light that the water has physically bent. This bending effect follows strict universal mathematical laws that make every shift in direction entirely predictable. The first law of refraction dictates that the incident light ray, the refracted ray, and the normal line at the point of incidence all exist on the exact same plane. By isolating the geometry of this plane, we can measure the angle where the incoming light arrives, the angle of incidence, and compare it to the angle where it leaves, the angle of refraction. This provides the basis for Snell's law. If you divide the sine of the angle of incidence by the sine of the angle of refraction, the result is a constant number for those two specific materials. To summarize the core principles, refraction is the bending of light. Entering a denser medium bends it toward the normal. Entering a rarer medium bends it away, and Snell's law ensures this relationship is mathematically consistent. That constant number generated by Snell's law functions as a unique identifier for every transparent material, known as the refractive index. Calculating this value allows us to predict and manipulate light with extreme precision, which we will explore in the next.
Have you ever noticed how a straw in a glass of water looks like it's been snapped in half or shifted to the side? That broken look is actually the result of a physical traffic jam. When light races through empty space, it moves as fast as physics allows, but hitting a new material, it instantly slams on the brakes. We often talk about the speed of light as a single unchanging limit, but that top speed of 186,000 miles per second only happens in a total vacuum. Anywhere else, light is forced to move slower. When a wave of light hits a slower material at an angle, one side of the wave slows down a fraction of a second before the rest. This uneven drag forces the light to pivot, pulling it off its original course. This change in direction, caused entirely by light changing its speed, is a phenomenon called refraction. To understand how light behaves in our world, we have to recognize that every transparent material acts as its own unique speed limit for light. Scientists measure these speed limits using a number called the refractive index, which we represent with the letter n. We calculate this index with a simple ratio. On the top of our equation, we put the letter c. This represents the absolute maximum speed of light in a vacuum, where nothing is in its way. On the bottom, we place the letter v. This is the actual restricted speed of light as it travels through a specific material, like a piece of plastic or a drop of oil. Because the top number is a constant, a slower speed on the bottom means the total score on the left grows. This leads to a simple rule. The larger the refractive index number, the slower light is actually moving. We can use this leaderboard to see how different materials rank as speed bumps for light. At the very top is air. With a score of 1.0003, it barely hinders light at all. Next is water, with an index of 1.33. This means water is thick enough to act as a moderate speed bump, slowing light down to about 3/4 of its maximum speed. Standard window glass scores a 1.52. Here, light faces even more resistance, and its speed drops significantly compared to its trip through a rain puddle. But the real outlier is diamond, with a massive 2.42. Light moves so slowly through a diamond that it's traveling at less than half its vacuum speed. Because light bends so sharply inside a diamond, it strikes the inner surfaces at angles, forcing it to bounce back inward. This internal bouncing channels the light, reflecting it off the inner walls like a hall of mirrors, until it exits through the top in those concentrated flashes of sparkle. Ultimately, the refractive index determines exactly how much light will bend, and the specific path it will follow through a material. It's tempting to think that if a material feels physically heavier or more solid, it must be harder for light to travel through. But physical weight and light speed don't always go hand in hand. We can see this by mixing kerosene oil and water. If you pour them into a jar, the kerosene floats right on top of the water. This is because kerosene is physically lighter. It has a lower mass density. Light has a harder time passing through kerosene. Even though it's physically lighter, kerosene has a higher refractive index of 1.44 versus water's 1.33. This shows two different types of thickness. Water has a higher mass density, but kerosene has a higher optical density. This reminds us that a refractive index is purely a measure of how much a material fights the passage of light,
and that resistance doesn't always follow the rules of physical weight. Every time light enters a new material, its speed determines its new path. Grasping this simple speed limit is what allows us to design the lenses in our cameras, the glasses on our faces, and telescopes looking into deep space. You open your eyes, and the world is a blur of indistinct shapes. But slide a precisely curved piece of glass in front of your face, and that chaos snaps into sudden clarity. We rely on these transparent tools constantly. They are in the smartphone cameras capturing our memories, the microscopes identifying cellular pathogens, and even the biological structures sitting right now inside our own eyes. But what actually makes them work? At its most basic level, a lens is just a piece of transparent material, like glass or plastic, bound by at least one curved spherical surface. If you look through a flat window pane, light passes straight through undisturbed. The geometry of the curve is what gives a lens its power, dictating exactly how light bends as it enters and exits the material. By engineering these simple geometric shapes, we can wrangle scattered light rays, allowing us to see further into space and deeper into the microscopic world than biology ever intended. Lenses fall into two structural categories. First is the convex lens. Notice how it bulges in the middle and tapers at the edges. Being thicker in the center makes it a converging lens. It bends parallel light rays inward, forcing them to meet. The concave lens has the opposite anatomy. It caves inward, making the middle thinner than the edges. This inverted shape is a diverging lens. Instead of pulling light together, the concave curve fans incoming rays outward, scattering them apart. In optics, form is function. The geometry of the glass acts as strict physical instructions that tell incoming light exactly where to travel. To predict where light ends up, physicists map the lens using basic coordinates. Dead center is the optical center, labeled O. Light passing through here doesn't bend. Next, we draw an imaginary horizontal line through O called the principal axis. Together, the optical center and principal axis create a reliable coordinate plane. We use this map to engineer exactly how a lens manipulates images. Bringing parallel light rays back to our convex lens, notice they intersect at one spot on the principal axis. This is the principal focus, F. Measuring the distance from the optical center to F gives the focal length, F. A diverging concave lens also has a principal focus, but it works backwards. Because the rays spread apart, the focus is the virtual point behind the lens where scattered rays appear to have started from. This focal length is a highly practical measurement. It's the exact physical distance camera manufacturers use to properly place a digital sensor, or optometrists use to correct for a retina, ensuring you capture a sharp image instead of a useless blur. To test the physical reality of that focal length, we can run a simple real-world experiment using the ultimate source of parallel light rays, the sun. If you take a standard convex magnifying glass outdoors on a clear day, you can align it directly between the sun and a sheet of dry paper. As sunlight hits the glass, the lens converges millions of massive light rays inward, forcing them to meet exactly at the principal focus. That blindingly bright dot you see on the paper is the physical manifestation of the focal length. It sits exactly distance F away from the lens. Light is energy. Forcing that much energy into a microscopic point generates immense destructive heat. Within moments, the paper smokes, chars, and ignites. In optics, finding focus is a physical act. It is the literal concentration of raw power into a single point in space. This graphic summarizes the rules of the glass. A convex lens bulges in the middle, converges light inward, and brings energy to a single point. The concave lens caves in at the middle, and it diverges or spreads light apart. Every time you read clearly through glasses or snap a perfect photograph, you are wielding these invisible laws of geometry to intercept light and bend reality to your exact specifications. Take a look at this diagram of a lens. While mirrors create images by bouncing light backward, lenses operate through a transparent medium. They use refraction, catching the light and bending it to form an image on the other side. Our goal today is to map a very specific pattern. tracking the exact seesaw relationship between where an object is placed and where its resulting image appears. By internalizing these geometric rules, we can accurately predict how optics behave in the real world, dictating the design of everything from a handheld magnifying glass to a sophisticated multi-lens camera. This diagram sets up our optical laboratory. Running through the middle is the principal axis. We track positions using the optical center in the middle, the primary focal points, f1 and f2, and the double distance markers, 2f1 and 2f2. We start with our object extremely far away, essentially at infinity. The lens converges all those incoming light rays to form a tiny, real, inverted image directly on the opposite focal point, f2. Now we push it toward the lens. As the object crosses inward toward the 2f1 marker, the image reacts by moving further away from the lens, growing larger in the process. The system hits a point of perfect symmetry right here. When the object sits exactly at 2f1, the image lands precisely at 2f2. The resulting image is real, inverted, and exactly the same size as the original object. Pushing past that point of symmetry, the image rapidly accelerates away from the lens. Once the object enters the space between 2f1 and f1, we get a highly enlarged real image stretching out far beyond 2f2. The pattern breaks when the object reaches the focal point, f1. The exiting light rays are bent so they run perfectly parallel to each other. Because they never intersect, the image effectively disappears into infinity. Sliding closer than the focal point flips the entire system. The lens stops projecting a real image on the far side and instead acts as a standard magnifying glass, creating a virtual, upright, and highly enlarged image on the exact same side as the object. The convex lens is highly dynamic, but you can master it by remembering one critical threshold, the focal point. That is the exact boundary where the image shifts from real and inverted to virtual and upright. The convex lens requires you to track 6 different scenarios based on distance. Let's see how much complexity we add when we switch to a concave lens. Look at this diagram of a concave lens, which is thicker at the edges than the middle. Instead of converging light, it diverges it, forcing the rays to bend away from the principal axis. Because the rays scatter, they appear to originate from a point on the same side as the object. Because of that constant divergence, the object's position hardly matters. No matter where it moves along the axis, the resulting image is permanently trapped between the focus and the optical center. It remains virtual, upright, and diminished. There are no complex charts to memorize here. The concave lens consistently produces a small, upright, virtual image. To map images, use 3 ray tracing rules. First, rays parallel to the principal axis always refract through the principal focus. Second, rays aimed at the focus emerge parallel. Third, rays passing straight through the optical center travel without deviation. You only need to draw 2 of these 3 lines. The exact point where those 2 rays intersect dictates the position, size, and nature of your image. Reviewing this summary chart gives us a clean divide. Convex lenses are highly variable and primarily project real images, while concave lenses are completely static, yielding only virtual, upright, and diminished images. Internalizing these visual patterns provides a baseline intuition for optics. By knowing exactly what the image should look like in your head, you have a built-in check for your work when you calculate the exact distances using the lens formula. The way lenses focus light into distinct images depends on a strict, unbreakable set of mathematical rules. To solve any problem involving spherical lenses, we rely on one primary tool, the lens formula. 1 over v minus 1 over u equals 1 over f. Let's map out these variables. U is the object distance, measuring the distance from the object to the optical center. V is the image distance, which shows where the lens projects the result. And f is the focal length, a fixed geometric property of the lens. Before calculating, we must apply the Cartesian sign conventions. We place the object to the left of the lens, meaning the object distance, u, is always a negative number. The focal length is positive for a convex lens and negative for a concave lens. Mastering these specific positive and negative sign assignments is the only way to ensure the math reflects the physical reality of the lens. Lenses also change the size of the objects they project. Magnification ratios allow us to calculate exactly how large or small an image will appear by comparing heights or distances. These numerical results describe the orientation of the image. A positive magnification means the image is virtual and erect. A negative magnification means it is real and inverted. We can apply this to a concave lens problem. If a lens has a focal length of 15 centimeters and we need an image to form 10 centimeters away, the image will appear on the left side of the axis. Therefore, v equals -10 and f equals -15. To find the object distance, u, we rearrange the formula to isolate 1 over u. Notice the signs here. Subtracting -1/15 results in a positive 1/15. Tracking these double negatives prevents calculation errors. Completing the math gives us an object distance of -30 centimeters. Dividing our image distance of -10 by that -30 results in a magnification of positive 0.33. This positive result means the image is virtual, erect, and 1/3 the size of the object. This algebraic process provides a precise way to predict the nature and location of an image without tracing out a physical ray diagram. Use these rules for a new problem. A 2-centimeter tall object is 15 centimeters from a convex lens with a 10-centimeter focal length. Pause the video now to identify the variables and assign their correct signs. The object stands above the axis, so h is positive 2.0. The convex lens has a positive focal length of 10, and the object distance, u, is -15. We find the image distance, v, by adding 1/10 and -1/15. Using 30 as the common denominator, we get 3/30 minus 2/30. This leaves us with an image distance of 30 centimeters. For the second phase, magnification is 30 divided by -15, which is -2.
Multiplying that -2 by our 2-centimeter object height results in an image height of -4.0 centimeters. Look at the final negative results. A magnification of -2 and a negative image height mean the image is formed below the principal axis, confirming it is real and inverted. A single missing negative sign at the start of your setup would change these results entirely, illustrating why sign conventions are the most important part of the process. While the lens formula tracks where an image forms, we also need to measure the optical strength of the lens itself. Lens strength is measured as power. P equals 1 over focal length. The unit is the diopter. A short focal length bends light sharply, creating a high power rating. Crucially, this focal length must be in meters. Using centimeters will make your diopter calculation incorrect. This summary board covers the essential tools for optics, the lens and magnification formulas, lens power, and the sign convention rules needed for any problem. By combining these formulas with strict sign rules and unit conversions, you can now solve complex optical problems using algebra alone.